On a January morning, the sea near Tonga split open, and a tower of ash punched all the way to the edge of space. You would have to go back more than 100 years to find a sound this loud. The blast reached Alaska, almost 6,000 miles away, carrying the force of hundreds of atomic bombs. This one volcano broke records nobody believed a volcano could touch. It fired the tallest plume ever seen. It sparked the most intense lightning ever measured. It sent waves racing across oceans that Tonga does not even reach. It tore a hole in the electric shell that wraps our planet. It even blasted enough water into the sky to bend the weather for years. If wonders like this pull you in, take a second to like and subscribe so you never miss one. Now take a slow breath. We begin. Picture a mountain taller than almost anything on land, and you cannot see it at all. Off the coast of Tonga, in the South Pacific Ocean, the water looks calm and empty, blue in every direction. A few small islands sit on the surface, low and green, home to seabirds and little else. For years, sailors passed them without a second thought. 2 tiny bumps of rock, nothing that looked dangerous, but those 2 islands were lying to everyone. They were the 2 highest points of one enormous mountain, and almost all of that mountain sat hidden underwater. From its base on the seafloor to the top of its rim, this volcano stands more than a mile tall. Stack it against buildings, and it would tower over the tallest skyscraper on Earth, with room to spare, and it is wide. The whole structure spreads about 12 miles across. If you dropped it onto a city, it would swallow the entire thing, downtown, suburbs, airport and all. Here is the strange part. The only pieces anyone could see were those 2 little islands, each smaller than a shopping mall parking lot. Everything else stayed under the waves, quiet, patient, out of sight. Scientists knew it was there. They had mapped it with sound, bouncing pings off the seafloor to draw its shape. What they mapped worried them. At the centre of the mountain sat a giant bowl. Volcanologists call this kind of bowl a caldera, and you can think of it as the scar left behind when a volcano blows its own top off and the ground caves in. This caldera was nearly 3 miles wide. Its floor rested about 500 feet below the surface of the sea, close enough to feel the sunlight, deep enough to hide a secret. The name people gave the whole thing was a mouthful. Hunga Tonga and Hunga Ha'apai were the 2 islands. Together, the mountain beneath them became known as the Hunga Volcano. Think of it as one sleeping giant with only its eyebrows showing above the water. Now, sleeping's the right word because this giant was alive. Volcanoes near Tonga sit along one of the most violent zones on the planet, a place where slabs of the Earth's crust grind and dive beneath each other. Heat builds, melted rock gathers, pressure climbs. This particular giant had erupted before in small bursts, and each time it did something strange. It built new land. Out of the open sea where there had been only water, the volcano pushed up fresh ground you could stand on. It had done this more than once, and the last time it happened, scientists got to watch it live. What they saw would teach them how this volcano worked. It would also fool them into thinking they understood it, because the calm you see on the surface tells you almost nothing about what is building far below. The sea can look like glass while something enormous shifts in the dark beneath it. By late in the year 2021, the giant had been feeding on melted rock for a long time, storing it, packing it in, waiting. And the first sign that something had changed was already close. In the final weeks of 2014, the sea between the 2 islands began to boil. Steam shot up. Ash blackened the sky. Chunks of a hot rock arced through the air and splashed down into the water. From a distance, it looked like the ocean had caught fire, and in the middle of all that chaos, something was being born. Day by day, a mound of ash and rock climbed out of the waves. It grew wider, it grew taller. Within weeks, a brand new island stood where there had been nothing but open water. Steam and falling ash slowly welded it to the 2 older islands on either side. 3 pieces of land became one. The map of that little corner of the Pacific had to be redrawn. Scientists could hardly believe their luck. New islands like this almost never last. Fresh volcanic ash is soft and loose, a little like a giant sandcastle. The ocean usually chews it up and drags it back under within days or weeks. Most of these baby islands vanish before anyone can study them. Researchers expected this one to melt away too. It refused to go. Rain and seawater soaked into the ash and hardened it, almost like wet cement setting into stone. The island held its ground. Month after month, it stayed. Then year after year. A team at the American Space Agency watched from orbit, fascinated because this was one of the first times they could track a new island from birth and follow it as it settled in. They gave the combined island a name built from the two older ones, Hunga Tonga and Hunga Ha'apai, and they studied it closely because a surviving island like this was a rare gift. Some researchers even thought it might teach them about places far beyond Earth. Here is why. On the planet Mars, scientists see old landforms that look like they were shaped by volcanoes erupting through water long ago. A young, wet volcanic island right here on Earth was the closest thing they had to a living example. By watching this one age, they hoped to read the ancient story written on another world. So the island became a kind of outdoor laboratory. Boots on the ground, cameras in orbit, measurements year after year. The volcano seemed calm now, almost friendly, a quiet mound of black rock slowly turning green as plants crept in. Birds moved onto it. Life took hold. Everything about it whispered that the danger had passed. The eruption that made the island had been the kind volcanologists called gentle. Steam and ash. A lot of noise, a modest amount of muscle. Nothing that threatened the wider world. If this was the worst the Hunga volcano could do, the people of Tonga had little to fear from it. But that reading rested on one quiet assumption, that the giant would keep behaving the way it always had. Underneath the new island, out of sight and out of mind, melted rock kept gathering, slowly, steadily, filling a chamber in the dark. Nobody could see how much was building up down there, or how much pressure it was under. The giant had spent years looking tame. It was almost done pretending. On the 19th of December 2021, the giant cleared its throat. A plume of steam and ash rose from the island and spread into a grey smudge across the sky. On Tonga Tapu, the main island of Tonga about 40 miles away, people looked up and saw it. Some grabbed their phones and filmed, a volcano putting on a show. It felt more like a spectacle than a threat. The eruption stayed noisy for days. Ash drifted. Small booms rolled across the water, and true to form, the volcano started building again. Fresh rock piled onto the island, making it bigger than before. To anyone watching, this looked like the same old giant doing the same old thing, loud, showy, and basically harmless. Then, in the first days of January, it went quiet. The plume faded, the booms stopped, the sky cleared. For about a week, the volcano rested and people relaxed. The show, it seemed, was over. Boats went back to their routes. Life on the islands rolled on. Whatever the giant had wanted to say, everyone assumed it had finished saying it. That silence was the most dangerous part, because underneath the calm surface, the volcano had a problem building, and to understand it, you need to picture what was happening far below the seafloor. Deep inside the mountain sat a chamber of melted rock. Scientists call melted underground rock magma. Think of it as the fuel tank of the volcano. That tank was full, and it was under enormous pressure, packed with trapped gas the way a shaken soda bottle is packed with fizz. For years, that pressure had a way to bleed off slowly, through small eruptions, gentle burps, a little steam, a little ash, and the tension eased. That was why the giant had always seemed tame. It let its pressure out in tiny, safe doses. Something about this time was different. The gas stayed trapped, the pressure kept climbing, and a full sealed magma chamber under a shallow sea is one of the most dangerous setups in all of nature. All that force needs is a single crack, a sudden weak point, and everything changes in an instant. Scientists watching from a distance could see the eruption had paused. What they could not see was the pressure still rising underneath. The tools to peer that deep in real time under a remote underwater volcano in the Pacific barely existed. The giant was building towards something huge, and the world was mostly looking away. On the 13th of January, the quiet broke. The volcano roared back to life stronger than before. The plume shot higher. The booms grew louder and sharper. This was bigger than December. Anyone watching could feel that the mood had changed. The giant had stopped clearing its throat. Now it was winding up. Through the 14th of January, the eruption kept climbing. Each blast seemed to top the last. Ash towered over the sea. The ground and the water trembled with the force of it. And still, the worst was yet to come. Everything so far, all the noise and smoke and fury, was only the giant taking a breath. The next morning it would let that breath out, and the whole planet would feel it. At about 5 in the evening local time, the sea near Tonga exploded. This time the giant skipped the warm-up. In one violent instant, the ocean surface tore open and a monster leaped into the sky. Ash, rock, steam and gas blasted upward all at once, faster than a jet, punching through the clouds and spreading into a vast dome. Within minutes, that cloud swelled to about 100 miles across. From space, satellites caught the whole thing. It looked like a grey flower blooming over the blue Pacific, wider than some entire countries. What triggered it happened in a heartbeat deep below. Remember the sealed chamber of melted rock, packed with trapped gas and under crushing pressure. Somewhere in the mountain, the rock finally cracked. And the moment it cracked, the pressure dropped, the way a shaken soda bottle erupts the instant you twist the cap. All that trapped gas expanded at once, blasting the magma apart. Then came the part that made this eruption so ferocious. The crack let seawater rush in. Cold ocean water poured straight onto scorching melted rock, and the two should never meet. When they do, the water flashes into steam in a fraction of a second, swelling to hundreds of times its size. That sudden burst of steam acts like a bomb. Scientists have a name for this kind of blast, where water and magma collide. They call it phreatomagmatic, which is a long word for a simple, terrifying idea. The sea itself became the fuse, and this was a shallow ocean sitting right on top of a giant gas-charged chamber. When they met, the explosion released the energy of millions of tons of dynamite in a single stroke. The blast threw a column of debris straight up at incredible speed. It ripped the island apart. The land that the volcano had spent years patiently building, the ground where birds had nested and plants had spread, was blown to pieces and hurled into the sky. In one moment, years of quiet construction were undone. Down in Tonga, people felt it in their chests before they fully understood it. A pressure, a boom, a shaking of the air itself. The sky over the ocean turned black and boiling. Purple lightning began to flicker inside the rising cloud, more and more of it, as if the plume were charging with electricity. This was the climax the giant had been building toward for weeks, maybe for years. And it was only getting started, because a blast this size sends out messengers in every direction, through the water, through the ground, and through the air. The first of those messengers was sound. A boom rolled outward from the explosion, low and immense, racing across the ocean at the speed of sound. It swept over the islands of Tonga. It kept going, out across open water, toward distant shores that had no idea what had just happened. That sound was about to travel farther than almost any sound in living memory. It would cross entire seas. It would reach a frozen coastline thousands of miles away. And people there would hear it with their own ears. In Alaska, nearly 6,000 miles from Tonga, people heard a strange, distant boom. They had no idea what it was. A far-off explosion, maybe. A sonic boom from a jet. Some folks reported doors rattling. Others felt a faint thump roll through the air coming from the south, from somewhere far out over the ocean. Only later would they learn the truth. The sound had come all the way from a volcano in the South Pacific, on the other side of the world. Stop and picture that distance for a moment. 6,000 miles is roughly the width of an entire ocean. It is farther than a flight from New York all the way to Rome, then partway back. A sound that travels that far and is still strong enough for human ears to catch is almost beyond belief. Most sounds fade within a mile or two. This one crossed the planet. Closer to the volcano, the boom was overwhelming. In the country of New Zealand, more than 1,000 miles away, people heard loud bangs that rattled their windows. Many thought a truck had crashed nearby, or that something had blown up down the street. They walked outside to look. There was nothing. The noise had travelled over 1,000 miles of open sea to shake glass in their homes. On the islands of Fiji, on Samoa, across a huge stretch of the Pacific, people heard the same thing. A deep rolling roar with no visible source. Scientists who study sound and shaking in the earth quickly realized they were looking at something historic. One government scientist put it plainly: This was probably one of the loudest events to happen anywhere on Earth in more than 100 years. Think about everything that has happened in the last century. Wars with enormous bombs, rockets launching, other volcanoes erupting, and still, this single blast may have been louder than nearly all of it. To find something clearly louder, scientists had to reach far back in time, to the year 1883, and to another volcano on the far side of the world. That eruption, in what is now Indonesia, was so loud that sailors nearly 100 miles away suffered burst eardrums. Its sound circled the globe. For almost 140 years, nothing had matched it. Now the Hunga volcano had joined that rare and terrible club. There is something haunting about a sound this big. A boom is really just a wall of pressure moving through the air, a pulse that pushes on everything it passes. When you hear a clap of thunder, you're feeling a tiny version of this. The Hunga blast created a pulse so powerful that it stayed loud enough to hear after crossing an entire ocean. The air itself carried the volcano's voice around the world, but the boom was only the messenger. While distant countries listened to that far-off roar, they could not see what the blast had done back at its source. The island where it all began had vanished. That morning, 2 islands and a bridge of new land had sat above the waves. Hours later, most of it was simply gone. And how a mountain erases its own peak in a single afternoon is where this story turns truly strange. Before the eruption, you could have stood on that island. You could have walked its black sand, felt the warm ground under your feet, watched birds wheel overhead. Photographs from early January show it clearly. A dark, rugged strip of land, green in patches, sitting in a ring of pale blue shallow water. It looked solid, permanent, like it had always been there and always would be. A satellite passed over the same spot a few days after the blast. Almost all of it was gone. Where the island had stood, there was open water. The new land the volcano had built over the past 7 years, blown away. Large pieces of the 2 older islands gone too. Only a few small scraps of rock still poked above the surface, lonely and battered. In one afternoon, the giant had erased most of its own visible body from the map. Picture that scale for a moment. This was land you could measure in square miles. Ground that had survived pounding waves for years, that had grown tough and rocky, that plants and animals had claimed as home. The explosion tore that solid ground apart. It launched much of it upward, breaking it into ash and rock and flinging it into the sky and the sea. Millions of tons of island thrown into the air like dust off a table. Where did all of it go? Some of it rained back down as ash, coating everything for miles around in grey grit. Some shot high into the atmosphere and drifted for days, and a great deal of it collapsed back into the ocean and slid down the steep sides of the underwater mountain into the deep. The island was scattered in 3 directions at once, up, out, and down. The middle of the volcano changed shape as well. Remember the giant bowl at its centre, the caldera, that had rested about 500 feet below the surface. After the blast, scientists mapped the seafloor again and found the bowl had grown deeper and wider. The floor had dropped by hundreds of feet in places. The eruption had scooped out the heart of the mountain and let the roof of the emptied chamber sag downward. The giant had, in a sense, partly swallowed itself. For the people of Tonga, the vanished island meant something chilling. If the volcano could destroy that much solid land in a single afternoon, then the force behind the blast was almost impossible to picture. This was a level of power far beyond the gentle steam eruptions everyone had grown used to. The tame giant had shown its true strength, and that strength was staggering. Scientists wanted to put a number on it, a real measure of the raw energy released when the island came apart. So they studied how much rock had been removed, how tough that rock was, and how high the eruption had thrown its cloud. They ran the calculations. The answer they came back with was hard to even say out loud, because the power behind this eruption would turn out to rival the most fearsome weapons humans have ever built. And when the comparison finally came, it stopped people cold. To measure the blast, scientists reached for the most powerful thing they could compare it to: nuclear bombs. The bomb that fell on the city of Hiroshima in 1945 is one of the most destructive weapons ever used. It flattened much of a city in an instant. Its energy is often used as a yardstick for terrible power, and when researchers at the American Space Agency worked out the energy of the Hunger eruption, they found it dwarfed that bomb completely. Their early estimate was staggering. The eruption released something like 10 million tons of explosive energy in its main blast. 10 million tons. The Hiroshima bomb was equal to about 15,000 tons. Do the simple math, and this eruption packed the punch of hundreds of those bombs, more than 500 of them going off at nearly the same time. Imagine that. Hundreds of atomic bombs unleashed in a single stroke, in one spot in the ocean. That is the kind of energy it took to blow an island apart and throw it into the sky. Now, a fair word about that number. Estimating the power of a volcano is tricky, and scientists were careful to say so. Their first figures ranged widely, from a few million tons of energy up to almost 20 million. As they studied the eruption more closely, they refined it, and some estimates settled lower, into the range of several million tons for the main explosion. Even at the low end, though, the story stayed the same. This was one of the most powerful natural explosions in a very long time. How long? For that, you have to look at other giant eruptions in history. The famous eruption of Mount St. Helens in the United States back in 1980 released roughly the energy of 24 million tons of explosive. The Hunger Blast was in the same terrifying league. Go further back to the monster eruption in Indonesia in 1883, and the energy climbs to around 200 million tons, one of the largest blasts in recorded history. The Hunger volcano stayed below that legendary level, yet it still stood among the true heavyweights. In fact, scientists called it the most powerful volcanic eruption the world had seen in about 30 years, since a huge eruption in the Philippines in 1991. Here is what makes these numbers even more unsettling. All of that energy was released underwater, from a volcano whose top barely reached the surface of the sea. Much of the force punched straight up into the sky. A great deal of it slammed into the ocean. And where a bomb fires once and is done, this volcano poured out its fury for hours, blast after blast, feeding the towering cloud above it. That raises the real question of this whole story. Why was this eruption so much more violent than the gentle ones that came before it? The gentle steam bursts had come from the same mountain, the same magma, the same shallow sea. Something about this time turned a tame giant into one of the most powerful explosions in a century. The answer was hiding underwater, in a deadly partnership between the melted rock and the ocean itself. And once you understand it, you understand why volcanoes like this one are so feared. A volcano on dry land is dangerous. A volcano just beneath the sea can be worse, and the reason comes down to a deadly partnership between fire and water. On land, when magma blasts out of a volcano, it meets the open air. The eruption can be violent, throwing ash and lava high into the sky. That is frightening enough. Add a shallow ocean on top, though, and you unlock a whole new level of destruction. Here is the simple version. Melted rock is scorching hot, far hotter than an oven, hot enough to glow. Seawater is cold. When a large amount of that cold water suddenly touches that superheated rock, it flashes into steam almost instantly, and steam takes up hundreds of times more space than liquid water. That sudden, explosive expansion acts like a hammer blow, shattering the magma into tiny pieces and blasting everything outward with tremendous force. You can see a tiny, harmless version of this in a kitchen. Flick a few drops of water into a pan of very hot oil, and it spits and pops violently. The water is turning to steam in a flash and jumping away. Now imagine that same reaction, but with an entire ocean pouring onto an underground furnace the size of a mountain. The pops become explosions powerful enough to level an island. Scientists call eruptions where water and magma collide like this phreatomagmatic, and the Hunger volcano performed one on a scale rarely ever seen. But there is a catch, and it is a strange one. Depth matters enormously. If a volcano sits too deep under the sea, the crushing weight of all the water actually holds the eruption down and smothers it, like a heavy lid clamped over a pot. The blast never gets to fully explode, and if a volcano sits fully on land, with no water nearby, it loses the supercharging power that the sea provides. There is a sweet spot in between, a just right depth where the water can rush in and flash to steam while the explosion still breaks free. The Hunga volcano sat almost perfectly in that sweet spot. Its caldera floor rested only about 500 feet below the surface, shallow enough that seawater could pour onto the magma and explode, deep enough that a huge amount of water was available to feed the reaction. It was, in the worst possible way, a perfectly built bomb. The ocean was the trigger, the fuel booster, and the fuse, all at once. This is why the eruption caught so many people off guard. The gentle steam eruptions of years past had come from smaller, slower meetings of water and magma, little sips. This time, a massive crack let the ocean flood in all at once, onto a full and gas-charged chamber. The partnership between fire and water turned from a slow simmer into a single, catastrophic blast. Understanding this helped scientists see why the eruption was so violent. It also raised a chilling thought. Many shallow underwater volcanoes are scattered across the world's oceans, and most of them are barely watched at all. For now, though, all eyes were on the cloud the Hunga blast had thrown skyward. It was rising fast, faster than seemed possible, climbing past the airliners, past the weather, toward the edge of the sky, and it had no intention of stopping there. When a volcano erupts, its ash cloud usually climbs a few miles into the sky and then flattens out. The Hunga plume kept going. Most big eruptions throw their clouds into a layer of the atmosphere where jet planes fly and weather happens. That is already high, around 7 miles up, the cruising height of an airliner. A truly massive eruption might push a little higher, into calmer air above the weather. For a long time, scientists thought that was roughly the ceiling. There was a limit to how high a volcano could fling its cloud. The Hunga volcano shattered that ceiling. Its plume rose to about 36 miles above the sea. Read that again slowly. 36 miles straight up, in a towering column of ash, water and gas. To picture it, stack more than 5 of the world's tallest mountains on top of each other, and you still would fall short of the top of this plume. Airliners cruise at 7 miles. This cloud climbed roughly 5 times higher than that. No volcanic plume had ever been measured reaching such a height. This was the tallest one on record. How do you even measure a cloud that high? Scientists use satellites parked far out in space, watching the Earth from different angles. By comparing the views from more than one satellite at the same moment, they could work out the height of the plume, a bit like how your 2 eyes judge how far away something is by seeing it from slightly different spots. Several teams ran the numbers. They kept arriving at the same astonishing answer. The cloud had punched far higher than anything they had seen before. To understand why this matters, you need to know how the sky is layered. The air above us is stacked in floors like a tall building. The bottom floor, where we live and where weather happens, is called the troposphere. Above it sits a calmer, drier floor called the stratosphere, home to the ozone layer and to cruising jets near its base. Almost every volcanic cloud stops somewhere in these lower floors. Getting a plume fully into the stratosphere already takes a giant eruption. The Hunga plume blew past the stratosphere entirely. It kept climbing toward the next floor up, a thin, cold, high layer that sits far above the reach of ordinary weather and even above the ozone layer. Volcanic clouds almost never touch that region. To send a plume that high, an eruption has to hurl its material upward with breathtaking speed and force, fast enough to punch through layer after layer of the atmosphere before slowing down. This is what makes the Hunga eruption stand out even among history's giants. Plenty of volcanoes have been powerful. Few, if any, in the age of satellites have thrown their cloud this high. The plume became a kind of record marker in the sky, a signpost showing just how much energy the blast had packed, and it hinted at something researchers were only beginning to grasp. This eruption had reached a part of the atmosphere that scientists rarely, if ever, get to study from a volcano. That high, thin layer the plume was entering has a name, and the moment the cloud crossed into it, the Hunga eruption made history in a way no volcano ever had before. It became the first one ever seen to break through into the edge of space itself. That thin, high layer the plume smashed into is called the mesosphere, and it is a place volcanoes are never supposed to reach. The mesosphere sits far above the clouds and the jets, starting around 30 miles up. It is a strange, cold, nearly empty region. This is where shooting stars flare and burn. When a meteor streaks across the night sky and glows, It is usually burning up right here, in the mesosphere, rubbing against the last thin traces of air before space begins. This layer is the border zone at the top of our atmosphere, the last floor of the building before you step out into the emptiness beyond. Volcanic clouds do not belong up there, ever. Between the calm stratosphere below and the mesosphere above, there is a kind of dividing line, a boundary in the sky that separates the two layers. Scientists call this line the stratopause. For as long as people had been watching volcanoes with satellites, no eruption had ever thrown its plume across that line. It stood like a ceiling that volcanic clouds simply could not reach. On the 15th of January, the Hunger plume crossed it. For the first time ever recorded, a volcanic cloud punched straight through the stratopause and pushed up into the mesosphere. Think about what that means. In all the years scientists had spent studying eruptions from space, watching mountains explode all over the planet, they had never once seen a plume climb this high. The Hunger volcano did something no volcano had ever been caught doing. It reached the doorstep of space. To send ash and water that high takes almost unimaginable force. The plume had to blast upward fast enough to break through the heavy lower air, then the stratosphere, then the dividing line above it, and still keep rising. Most of the material eventually settled lower, spreading out in the calmer layers below. But the very tip of that monstrous column tagged the mesosphere before it fell back. Why does a detail like this matter so much? Because it rewrote what scientists believed a volcano could physically do. The height of a plume is a direct clue to the power of the blast beneath it. A cloud in the mesosphere is a receipt for an eruption of extraordinary violence. It told researchers, in the clearest possible way, that they were dealing with a genuine monster, one that pushed past the known limits of its kind. It also meant the eruption had delivered its cargo far higher than usual, and that cargo would matter enormously in the days and months to come. Because the Hunger plume carried something unusual inside it. Along with the ash and gas, it lifted a staggering amount of water high into the sky. Water that would linger there and quietly reshape the atmosphere for years. That part of the story is still unfolding, and we will come back to it. For now, the plume kept churning above the ocean, a black tower miles wide and dozens of miles tall, flickering with an eerie light. Because inside that giant cloud, another record was being set at the very same time. The plume had become a machine for making lightning, and it was about to produce a storm unlike anything ever measured on Earth. Inside the towering plume, the sky began to crackle with a fury scientists had never witnessed. Lightning is usually the work of ordinary thunderstorms. Hot, wet air rises, ice and water churn inside a cloud, and static electricity builds up until it discharges in a brilliant bolt. You have seen it 1,000 times on a stormy night. A flash, then the rumble of thunder. A big thunderstorm might crackle with lightning many times a minute, and that already feels intense. The Hunger plume made that look gentle. As the eruption roared, the giant cloud above it turned into a lightning factory running at full blast. Bolt after bolt tore through the ash and steam, so many and so fast that they blurred together into an almost constant flicker. Over the whole eruption, the plume produced close to 200,000 flashes of lightning, 200,000 from a single cloud, over a matter of hours. Researchers who study volcanoes and storms had simply never seen numbers like it. But how does a volcano make lightning at all? It comes down to collisions. When a volcano erupts, it blasts out countless tiny bits of ash and rock, along with water that quickly freezes into ice high in the cold cloud. Inside the churning plume, all these particles smash into one another over and over, rubbing and bumping like socks tumbling in a dryer. That constant friction strips away tiny electric charges and piles them up. When enough charge gathers, it releases in a violent spark. Lightning. A normal thunderstorm has water and ice to work with. The Hunger plume had all of that, plus a colossal load of ash, plus more water than almost any storm on Earth, all slamming together at once. It was the most electrically charged cloud imaginable, and it discharged that charge again and again and again. A scientist who led the study of this storm described it in vivid terms. She called it a supercharged thunderstorm, the likes of which had never been seen, and she meant that literally. Her team gathered lightning data from several different detection systems around the world. some listening for the radio crackle that lightning gives off, some watching from space. They combined all of it to peer inside the plume, using the flashes like flickers of light in a dark room, each one briefly revealing the shape of the monster. What the lightning showed them was remarkable. The flashes clustered in rings and waves that pulsed outward from the heart of the eruption, tracing the hidden structure of the plume. By reading the lightning, scientists could tell when the eruption surged and when it eased. The storm became a kind of natural instrument, writing the story of the blast in strokes of electricity, and the sheer intensity of it kept climbing. At the peak of the eruption, the lightning reached a rate so extreme that it would set a world record, a level of electrical fury that outstripped the wildest storms ever documented, including monster hurricanes and the fiercest thunderstorms on the planet. To grasp just how intense that peak really was, you have to count the flashes minute by minute, and the number scientists landed on was so high it almost sounds made up. At the height of the storm, the hunger plume threw down about 2,600 flashes of lightning every single minute. Sit with that for a second. 2,600 bolts of lightning in 60 seconds. That is more than 40 flashes every second, faster than you could ever count, a strobe light of raw electricity firing inside a cloud, dozens of miles tall. If you'd been able to watch it safely from space, the top of the plume would have shimmered and pulsed like a living thing, glowing from the inside with non-stop bursts of light. Nothing humans had ever measured came close. Before this, the most intense lightning storm on record was a powerful thunderstorm over the southern United States back in 1999. At its wildest, that storm produced a little under 1,000 flashes a minute. For years, that stood as the benchmark for the most electrically violent storm ever recorded. It seemed like an extreme that would be hard to beat. The hunger plume beat it by more than double, 2,600 flashes a minute against roughly 1,000. This eruption smashed the old record, leaving the previous champion far behind. And it did all of this from a single volcanic plume rising out of the ocean at one spot on the map. Why was this cloud so much more electric than any storm? The answer goes back to what was inside it. An ordinary thunderstorm builds its charge from water and ice alone. The hunger plume had those, and then it added something no thunderstorm has. Enormous amounts of volcanic ash and a staggering load of water flashed to steam and lifted high into the freezing upper air, where it turned to ice. More particles meant more collisions. More collisions meant more charge. More charge meant more lightning. The volcano had built the perfect engine for making electricity, and it ran that engine at full throttle for hours. There was another shock hiding in the data. When scientists mapped where all these flashes were happening, they realized the lightning was reaching astonishing heights. Some of it fired near the very top of that towering plume, at altitudes where lightning had never been recorded before. Bolts were sparking in a part of the sky no one had ever seen lightning reach. This was electricity climbing to record heights, inside a plume already climbing to record heights. And the flashes seemed to be doing something even stranger up there. They appeared to be riding along on top of huge ripples moving through the plume, sparking in rings that spread outward like the surface of a pond after a stone drops in. That detail hinted at forces inside the cloud that scientists were only starting to understand. Because the plume was pulsing, rippling and heaving with giant waves of pressure, and the lightning was surfing those waves, higher and farther than any lightning ever caught on record. To see how, we have to look closer at those strange invisible ripples racing through the cloud. The lightning near the top of the hunger plume was sparking higher than any lightning ever recorded, roughly 12 to 19 miles above the sea. To put that in view, ordinary lightning happens down low, inside storm clouds that sit a few miles up. The bolts you see from your window flash far below the height where jets fly. The hunger plume was throwing lightning at more than twice the altitude of a cruising airliner, in thin, frigid air near the edge of the stratosphere. Lightning had simply never been seen that high before. This was a brand new record, born inside an already record-breaking cloud, and the flashes were behaving in a way that puzzled scientists. The lightning was arranging itself into vast rings, spreading outward from the center of the plume. Picture dropping a stone into a still pond and watching circles ripple away from the splash. The lightning was tracing rings like that, but on a colossal scale, miles wide, high in the sky. Something inside the plume was making those ripples, and the electricity was riding along on them. Those ripples have a name. Scientists call them gravity waves. Do not let the word confuse you. In the sky, a gravity wave is just a ripple in the air, made when the air gets pushed upward and then sinks back down, bobbing like the surface of the ocean. When a violent eruption punches a plume upward, the air overshoots, then sinks, then rises again, sending giant ripples racing outward through the cloud. The hunger plume was heaving with these waves, and the lightning was surfing them, flash after flash lighting up the crests as they rolled by. By reading these patterns, scientists learned something they had missed. The lightning acted like a hidden clock ticking through the whole eruption. When the researchers followed the flashes carefully, they discovered the blast had lasted far longer than anyone first believed. The most violent phase went on for at least 11 hours, hours longer than early reports had suggested. The volcano had raged through the evening and deep into the night, and the lightning had recorded every surge. This turned out to be more than a curiosity. Watching a volcano through its lightning gave scientists a powerful new tool. A giant ash plume is dangerous to aircraft, and it often hides the volcano from view, making it hard to track from satellites alone. But lightning can be detected from thousands of miles away at the speed of light, even when the cloud blocks the view from above. By listening for the crackle of flashes, scientists could follow an eruption as it happened, almost in real time, and warn planes to steer clear. So the storm inside the hunger plume did more than break records. It taught researchers a smarter way to watch dangerous volcanoes in the future. But the lightning and the towering cloud were only part of what the eruption unleashed. Far below the flashing plume, the blast had punched the air itself with a single enormous shove, and that shove was now racing across the entire planet faster than any storm, as a wave of pressure the whole world would soon detect. The explosion did more than make noise. It slammed the entire atmosphere like a fist hitting a drum, and the ripples spread across the whole planet. When the hunger volcano erupted, it shoved a huge volume of air outward all at once. That shove created a wave of pressure, a moving wall where the air was squeezed slightly tighter, rolling outward in every direction from the blast. You cannot see a wave like this, but sensitive instruments can feel it as a small, sharp change in air pressure passing by. This pressure wave took off across the Earth at about the speed of sound. That is roughly 700 miles an hour faster than a passenger jet. The wave swept outward from Tonga in a giant expanding ring, like the ripple from a stone tossed into a pond, except the pond was the entire atmosphere of the planet. It raced across the Pacific Ocean. It crossed continents. It rolled over cities, deserts and seas, passing over billions of people who felt nothing at all as it went by. Then it did something that stunned scientists. It wrapped all the way around the world. The wave travelled from Tonga, spread across the globe, and met itself on the far side of the Earth, near a point directly opposite the volcano. Then it kept going, circling back toward home, and it did not stop there. Over the days that followed, the pressure wave went around the planet again, and again, looping the entire Earth at least 5 times before it finally faded away. Picture that journey. A single pulse of pressure born from one volcano in the South Pacific, travelling around the whole world more than 5 times. Each lap covered about 25,000 miles, the full distance around the Earth. Weather stations everywhere caught it, ticking off each pass as the wave rolled through like clockwork, days after the eruption itself had ended. How could one blast do that? The answer lies in how powerful the shove really was, and in how the atmosphere carries certain waves with very little loss. In the thin skin of air wrapped around our planet, a strong enough pressure pulse can travel enormous distances without dying out, sliding along the layers of the atmosphere. The hunger blast was strong enough to set the whole air envelope of the Earth ringing, like a bell struck once that keeps humming for a long time afterward. Scientists had read about events like this in history books. The last time a volcano sent a pressure wave circling the globe like this was well over 100 years earlier, from that same legendary eruption in Indonesia in 1883. Back then, people tracked the wave using simple weather instruments, and were amazed to see it pass several times. Now, more than a century later, the hunger volcano had done it again, and this time the whole world was watching with far better tools. That global pressure wave has a special name, and tracking it did more than fill the history books. It revealed a hidden danger, one that would soon reach out and touch oceans on the other side of the planet, in a way that made no sense at first. That planet-circling pulse of pressure has a name. Scientists call it a lamb wave. A LAM wave is a special kind of pressure wave that hugs the surface of a planet and travels along it, close to the ground, while most of its energy stays low instead of shooting up into space. Think of it as a wave that skims along the floor of the atmosphere as it races around the world. This is the wave that looped the Earth again and again after the hunger blast. And the remarkable thing is how many people, without even knowing it, recorded it in their own backyards. All around the world, instruments twitched at almost the exact moment the wave predicted. Weather stations, both at official observatories and in the homes of ordinary hobbyists, measure the pressure of the air. Normally that pressure drifts up and down slowly over hours as weather changes. When the LAM wave arrived, barometers everywhere showed a quick little jump, a tiny spike, and then a settling back, all within a few minutes. The blip was small, but it was unmistakable, and it appeared right on schedule as the wave swept through each region. People began comparing notes across countries. Someone in Europe would see the spike on their home weather station. Someone in North America saw it too at a slightly different time, matching the wave's steady march across the globe, then again as it came back around. It became one of the most widely recorded single events in the history of weather watching, captured by professional scientists and curious families alike, all reading the same faint fingerprint of a volcano half a world away. Why did this matter so much to scientists? Because it was the first time a wave like this had been captured in such stunning detail. Back in 1883, when the Indonesian eruption sent its own wave around the Earth, instruments were simple and few. This time, the planet was blanketed with sensors, thousands of them, feeding data every second. For the first time, researchers could watch a global pressure wave in crisp, complete detail, tracking its speed, its shape, and its strength as it circled the world. That detailed record turned out to be a goldmine. The LAM wave taught scientists how energy from a single explosion can spread through the entire atmosphere. It gave them a rare, real-world example to test their ideas about how the air behaves on a planetary scale. Events this clear come along perhaps once in a lifetime or less, and this one was measured better than any before it. But the LAM wave did something far stranger than tick barometers. As it swept across the world's oceans, this wave of air pressure pressed down on the water beneath it. A moving wall of pressure, gliding over the sea, and where it passed, it began to nudge the ocean itself, gently shoving the water along as it went. The air was reaching down and touching the sea. That should not have been able to cause a tsunami on the far side of the world. Yet, impossibly, it did. Because when the water around Tonga rose up and struck the shore, that was only the beginning of a tsunami story that would break the rules scientists thought they understood. The sea was about to rise in places it had no business rising at all. Near Tonga, the sea reared up and crashed ashore with terrifying speed. When the volcano exploded, it hurled water outward and dropped huge amounts of rock and ash into the ocean all at once. The sea had to go somewhere. It rose into towering waves and raced toward the nearby islands of Tonga. In some spots along the coast, the water surged as high as a 5 or 6 story building, roughly 60 feet, sweeping over beaches and into villages. People ran for higher ground as the ocean chased them inland. The waves battered homes, tossed boats, and flooded low-lying land. Sadly, several people lost their lives, and many more were hurt or left without shelter. For a small island nation, the damage was severe. Ash rained from the sky at the same time, turning day into an eerie grey twilight and coating everything in grit. It was a disaster on every front at once. Then the tsunami spread outward, across the whole Pacific Ocean. Warnings lit up around the entire ocean basin. In Japan, thousands of miles away, officials told people near the coast to move to higher ground, and waves did arrive strong enough to damage boats. Along the coasts of Chile and Peru in South America, the sea rose and rushed in, and tragically, the waves there took lives as well. In California, on the west coast of the United States, harbours sloshed and surged. In New Zealand, Hawaii, and island after island across the Pacific felt the water rise. A tsunami crossing an entire ocean is frightening enough on its own. This one carried a puzzle inside it. Normally, a tsunami is born when the seafloor suddenly jolts, usually during a big earthquake. The ground drops or lifts, the water above it heaves, and waves roll outward. The hunger tsunami came a stranger way. Several forces shoved the ocean all at the same moment. The explosion itself punched the water. The island collapsing into the sea displaced even more. Landslides of rock sliding down the underwater mountain added still another push. All of it combined to launch the waves, with no giant earthquake needed. Scientists have a name for the study of how tsunamis are born. They call it tsunami genesis, a big word for a simple question. What made the wave? For the hunger event, the answer was a tangle of causes working together, which made it unusually tricky to understand. And yet, even all of those causes combined left something unexplained, because tide gauges and sensors were picking up tsunami waves in places that made no sense. The waves arrived at some far-off coast too early, faster than a normal tsunami could possibly travel across the water. Something was rushing the ocean along, helping the waves outrun the speed they should have had. It was as if the sea had a secret partner, pushing it from above. That partner, of course, was the wave in the air. The pressure wave racing around the planet was pressing on the ocean as it went, stirring up water far from Tonga, sending waves towards shores the ordinary tsunami had not even reached yet. The atmosphere and the ocean were working together in a way scientists rarely get to witness, and that partnership was about to do something that seemed flatly impossible. It was about to raise tsunami waves in oceans that Tonga does not even connect to. Thousands of miles from Tonga, in an ocean the Pacific does not even touch, the water began to move. Look at a map for a moment. Tonga sits in the Pacific Ocean, the vast body of water on one side of the globe. On the other side lies the Atlantic Ocean, separated from the Pacific by whole continents. And tucked between Europe and Africa sits the Mediterranean Sea, a nearly closed pool of water linked to the Atlantic by only a narrow gap. A tsunami born in the Pacific has no water pathway to reach these places. The land blocks the way completely, yet sensors in the Atlantic and the Mediterranean clearly recorded tsunami waves after the hunger eruption. Read that again, because it sounds impossible. Water rose and fell in seas that a Pacific tsunami could never reach by travelling through the ocean. In the Caribbean, along Atlantic coasts, and in the Mediterranean, tide gauges caught the telltale rise and swing of tsunami waves, arriving in the hours after the blast. For a while, it looked like the ocean had broken the laws of geography. So how did water in the Atlantic feel a volcano in the Pacific? The answer was that giant wave of air pressure, the one circling the whole planet. As the pressure wave swept over the Atlantic and the Mediterranean, it pressed down on those waters just as it had pressed on the Pacific. A moving wall of air, gliding across the sea, nudging the surface as it passed. That push was enough to set the water rocking and to raise small tsunami waves in seas far from Tonga. The volcano reached those distant seas through the sky. A wall of moving air did the pushing, and no drop of Pacific water ever had to arrive. This had almost never been documented before. Scientists had long suspected that a violent enough eruption could stir tsunamis around the globe through the air, but they had never captured it clearly on modern instruments, all over the world at once. The hunger eruption gave them the first crisp, planet-wide recording of a tsunami driven by the atmosphere. Waves in one ocean, triggered by pressure from a volcano in another. It was a first in the age of modern science, and it forced scientists to rethink how they warn people about tsunamis. For decades, tsunami warnings have focused on earthquakes shaking the seafloor. The hunger event proved that a volcano, through the air alone, can raise dangerous water in places no earthquake ever would. It revealed a blind spot, a whole category of tsunami that older warning systems were not built to catch. Coastlines far from any volcano could, in rare cases, still be at risk. Think about what this one eruption had now done. It had crossed an entire ocean as sound. It had circled the planet as a wave of pressure over and over, and it had reached across continents to raise the seas in oceans it could never touch by water. A single volcano had stirred nearly every corner of the globe. Yet even the scientists who confirmed these impossible waves were left with a deeper question. How can thin air reach down and lift a heavy ocean at all? The answer involves two different waves, chasing each other around the world, and a trick of timing that let the sea outrun its own speed limit. To see it, we have to follow the exact moment the air first grabbed the water. To understand how thin air can lift a heavy ocean, picture two waves chasing each other around the world. When the pressure wave raced away from Tonga, it did two things to the sea at once. First, it pushed directly on the water beneath it, dragging a small bulge of ocean along underneath the moving wall of air. This travelling bump kept pace with the pressure wave itself, gliding across the sea at about the speed of sound, roughly 700 miles an hour. Scientists sometimes call this the locked wave, because it stays locked to the air pressure as it moves. Then a second kind of wave came into play. Once the water got shoved, it wanted to move on its own, the way any ocean wave does. But ordinary ocean waves travel much slower than the air wave that started them. So a set of slower waves trailed behind, moving at the normal pace of a tsunami through deep water, several hundred miles an hour. These are the free waves, released to travel by their own rules. Here is where the timing trick comes in. The fast, locked wave, riding along under the air pressure, could reach a distant coast far sooner than a normal tsunami ever would. That is why sensors on faraway shores picked up water moving too early. The ocean seemed to break its own speed limit, because the air was carrying it along, faster than water alone can go. Then, later, the slower free waves would arrive, the ones behaving like a regular tsunami. So many coastlines felt the sea rise twice, in a strange, staggered pattern. An early nudge from the air-driven wave, then a later push from the ordinary ocean waves. To scientists watching their instruments, this double arrival was a clear signature that something rare was happening. The atmosphere and the ocean were dancing together, one leading, one following. This partnership grew even stronger in certain places. When the fast air-driven wave passed over undersea mountains, deep trenches, or other big bumps on the seafloor, it could shake loose extra waves, adding new pushes to the water. The rough shape of the ocean bottom acted like a set of speed bumps, and each one spun off more ripples. The result was a tangled, worldwide pattern of waves, far messier and more widespread than any earthquake tsunami. Scientists had suspected for years that a giant eruption might work this way. The Hunger event handed them the proof, recorded in crisp detail all over the planet, and it left them with a sober lesson. A volcano can raise the sea through the air, far from its own shores, in ways that older tsunami warnings never accounted for. Understanding this could someday save lives on distant coasts. But while the world marvelled at waves in far-off oceans, something even more violent was unfolding much closer to the volcano, hidden completely from view. Down on the dark sea floor around the mountain, the eruption had triggered a monster of a different kind. A tidal wave of rock and ash was tearing across the bottom of the ocean, moving faster than any underwater flow ever recorded. And it was headed straight for something that connected Tonga to the rest of the world. While the sky above the volcano flashed and roared, an unseen avalanche was racing across the seafloor below. When the eruption blasted its towering column upward, much of that ashen rock could not stay in the air forever. Gravity pulled it back down. A huge amount of it crashed into the sea and slid down the steep underwater slopes of the mountain. Picture a landslide, but happening underwater, in the dark, made of a churning mix of rock, ash, and gas. Scientists call this kind of underwater avalanche a density current, because the heavy, debris-filled water flows downhill through the lighter water around it. On land, volcanoes make something similar, called pyroclastic flows, deadly clouds of hot ash and rock that rush down a mountainside. People have studied those for a long time. But almost no one had ever measured what happens when an enormous amount of volcanic material dumps straight into the ocean and races across the seafloor. The Hunger eruption gave scientists their first real chance to study one, and the speed they discovered was staggering. The flow tore across the bottom of the sea at about 76 miles an hour. That is faster than cars race down a highway, all of it happening underwater, in total darkness, deep beneath the waves. It was the fastest underwater flow ever recorded by scientists. A river of rock and ash, moving at highway speed across the floor of the ocean. How could anyone measure the speed of something no one could see? The answer came from a clever piece of detective work, and from something the flow destroyed along the way. As the avalanche raced across the seafloor, it slammed into cables lying on the bottom, snapping them. Each cable broke at a known spot at a known moment. By lining up where the breaks happened and exactly when, scientists could work out how fast the flow must have been moving, to travel from one break to the next. The destruction itself became a stopwatch. What they calculated amazed them. This was not a gentle settling of ash drifting down through the water. This was a powerful, fast, punishing flow with enough force to reshape the seafloor and destroy heavy equipment in its path. It carried an astonishing amount of material, scouring the ocean bottom as it went, dragging rock and ash for mile after mile away from the volcano. The flow reached far. It travelled more than 50 miles from the volcano before finally losing its energy. 50 miles of seafloor raked by an underwater avalanche moving at the speed of a race car. For scientists, this was a brand new kind of hazard, one they had barely known to look for. Underwater flows like this could threaten anything resting on the seafloor across a huge area around an erupting volcano. And the modern world has placed something very important down there, something entire nations depend on. Because the flow had not simply raced across empty ocean bottom, it had crossed the seafloor near Tonga, and buried in that seafloor lay the thin lifelines that connected the island nation to everyone else on Earth. When those lifelines snapped, a whole country went dark. The underwater avalanche did something that should not have been possible. It climbed. You would expect a flow of heavy rock and ash to behave like water, always running downhill and settling in the lowest spot it can find. That is what gravity does. Heavy things flow down. And for most of its journey, that is exactly what the hunger flow did, pouring down the steep sides of the volcano into the deep. But then it hit rising ground, and it kept going anyway. Tonga's main international cable lay in a valley on the seafloor south of the volcano. Between the volcano and that cable stood underwater ridges, raised humps of seafloor blocking the path. A weak flow would have stopped when it reached them, unable to climb. The hunger flow had so much power and so much speed that it charged straight up and over those ridges, then rushed back down the other side and slammed into the cable beyond. Scientists who study the seafloor were amazed. For a flow to run uphill, over huge ridges, and still have the force to break a cable on the far side, it had to be carrying an almost unbelievable amount of energy. This was one of the most powerful underwater flows ever witnessed, strong enough to ignore the usual rules about heavy things only going down, just how much material was on the move. When research ships later mapped the seafloor around the volcano, they found the eruption had torn loose and rearranged a staggering volume of rock and ash. Something like 10 cubic miles of material had been remobilized across the seabed. 10 cubic miles! Imagine a block of rock and ash a couple of miles wide, a couple of miles long, and more than a mile tall, all of it ripped up and dragged across the ocean floor. That is the scale of what the eruption moved down in the dark. The evidence was written all over the seafloor. In one spot, scientists found Tonga's domestic cable buried under about 100 feet of fresh volcanic debris. 100 feet of rock and ash dumped on top of a cable by a single event. When they sampled that debris, it clearly showed the marks of a fast, powerful seafloor flow. The proof was right there, packed on top of the broken line. The team leading the mapping said the eruption kept ticking record after record off their list. The tallest plume, the globe-circling pressure wave, the loudest blast in over a century. And now the fastest underwater flow ever measured, powerful enough to run uphill. Each new discovery added to a portrait of an eruption that broke limits in nearly every direction at once. For the people of Tonga, though, this seafloor drama was more than a scientific marvel. It struck at something they needed every single day. Those cables buried and snapped on the ocean floor were how Tonga talked to the world. Phone calls, messages, the internet, banking, news, all of it flowed through thin lines resting on the seabed. When the flow tore through them, it did more than break some wires. It cut an entire nation off from the rest of the planet at the worst possible moment. In the hours after the eruption, Tonga simply went quiet, as if the whole country had vanished from the world. To grasp how this happened, you have to know how islands like Tonga stay connected. Almost all of the world's internet and phone traffic does not travel through space by satellite. It runs through cables lying on the ocean floor, thin lines wrapped in protective layers, stretching for thousands of miles across the seabed. For a remote island nation, often a single main cable is the lifeline linking it to everyone else. That one line carries the calls, the messages, the internet, the banking, nearly everything. The hunger eruption cut that lifeline. The fast, powerful underwater flow that raced across the seafloor snapped Tonga's cables, both the international line reaching out to the wider world and the domestic line linking its own islands. In an instant, the country lost its main connection to the internet and to overseas phone networks. People could not easily call loved ones abroad. Families in other countries could not reach their relatives in Tonga to learn if they were safe. Imagine the fear on both sides. Outside Tonga, people watched news of a massive volcanic eruption and a Pacific-wide tsunami, then found they could not contact anyone on the islands at all. Inside Tonga, people were dealing with ashfall, flooded coasts and damaged homes, while also cut off from the outside world, unable to easily send word that they had survived. The silence stretched on, heavy and frightening for days. Fixing the damage was slow and hard. Repairing an undersea cable is a major operation. A special ship has to sail out, find the exact spot where the cable broke, sometimes miles deep, haul the ends up from the seafloor and splice them back together. When officials assessed the damage, they warned it could take weeks to restore the main connection, and that was on top of the danger that more of the seafloor might still be unstable near the volcano. In the meantime, Tonga leaned on backup methods to reach the outside world, patchy and limited though they were. Satellite links helped carry some urgent communication, a slow trickle compared to the flood of data a cable normally handles. Bit by bit, word got out that the nation had survived the blast, even as full service stayed broken for a long stretch. This part of the story carried a warning far beyond Tonga. The modern world runs on these undersea cables, and most people never think about them. They rest quietly on the seafloor, out of sight, carrying almost everything. The Hunger eruption revealed how a single natural disaster could sever those lines and isolate an entire country in moments. It exposed a fragile thread that civilization depends on, and it showed how a volcano can reach up from the deep to cut it. The eruption had now touched the sea, the air, and the wired connections that tie us together. It had reshaped coastlines and buried cables under mountains of debris, and it had rearranged the very floor of the ocean around the volcano. When scientists finally went back to map what the blast had done to the seabed itself, they found the mountain had been remade, carved and reshaped by its own fury in ways that stunned them. Months after the eruption, research ships sailed out to map the seafloor around the volcano, and what they found barely matched the old maps at all. Before the blast, scientists had a good picture of the mountain. They knew the shape of its giant central bowl, the depth of its slopes, the lay of the seabed around it. After the eruption, they went back with sound mapping equipment, bouncing pings off the bottom to redraw its shape in detail. When the new maps came in and they compared them to the old ones, the difference was jaw-dropping. The volcano had partly erased and rebuilt itself. Remember the caldera, the huge bowl at the center of the mountain, which had rested about 500 feet below the surface. After the eruption, the floor of that bowl had dropped much deeper in places, sinking by hundreds of feet. The blast had emptied out part of the magma chamber below, and the ground above had sagged downward into the space left behind. The heart of the volcano had caved in on itself. Around the mountain, the story was just as dramatic. The eruption had stripped away material in some places and piled it up in others. Whole stretches of the seabed were buried under thick blankets of fresh volcanic debris. In some spots 100 feet deep or more, deep channels had been carved by the racing underwater flows, like gullies gouged into a hillside by a flood, except these were on the floor of the ocean, cut in a single violent day. The gentle old slopes were scarred and reshaped. In total, that enormous volume of material had been torn up and moved, around 10 cubic miles of it. To picture that, imagine scooping up a chunk of earth big enough to bury a large city under a mountain of rubble, then dragging it across the seafloor and dumping it in new places. That is the kind of earth-moving the eruption did. All underwater, all in hours. Scientists rarely get to see changes like this so clearly. Most underwater eruptions happen far from any instruments, and the seafloor changes go unmapped. Because this volcano had been studied before the blast, researchers had a rare before and after view. They could measure exactly how much had shifted, where the ground had dropped, where debris had piled up, how the flows had carved their paths. It was like watching a landscape get rebuilt and being able to measure every scar. This mapping did more than satisfy curiosity. It helped scientists understand how these violent underwater eruptions actually work, how the mountain empties, collapses and reshapes itself, and how the debris travels. That knowledge could help them judge the dangers at other underwater volcanoes around the world, many of which have never been mapped at all. The Tonga volcano had now shown its power across the ocean, through the air, and deep on the seafloor. Yet the eruption's reach did not stop at the top of the sky either. Far above the plume, far above the clouds and the jets, high in the electric layer where the atmosphere fades into space, something extraordinary was happening. The blast had reached up and torn a hole in the very edge of our planet's atmosphere. High above the eruption, in a layer of the atmosphere most people never think about, the blast punched a hole. Far above the weather, above the height where jets fly and even above where the plume reached, there is a region called the ionosphere. Here the thin air is charged with electricity. Sunlight is so strong at this altitude that it knocks tiny pieces off the atoms of gas, leaving the air electrically active, full of charged particles. This electric layer wraps around the entire planet, and we depend on it more than we realize. Radio signals bounce off it. Signals from navigation satellites pass through it to reach the devices we use to find our way. The Tonga eruption reached up and disturbed this electric layer in a big way. When the shock waves and pressure waves from the blast pushed upward through the atmosphere, they kept climbing, all the way into the ionosphere. There, near the volcano, they tore open a large gap in the charged particles, a region where the electric content of the air suddenly dropped far below normal. Scientists described it as a hole punched in the ionosphere, a depletion spreading across a wide area of the sky above Tonga. Think about the reach of that. A volcano at the bottom of the ocean sent its energy so high that it disturbed the electrified edge of the atmosphere, the border zone where our air fades into space. Very few natural events on Earth ever touch that layer. Big eruptions, powerful earthquakes, and certain storms can send faint ripples up there. Rarely does anything punch a clear hole in it. The Tonga blast did. How did scientists spot a hole in an invisible electric layer? They used the signals from navigation satellites, the same network that powers the maps on our phones. When those signals travel down through the ionosphere, the charged particles along the way change the signal in tiny, measurable ways. By studying signals from many satellites and ground stations at once, scientists can map how much charge is in the ionosphere across huge regions. After the eruption, their maps showed a clear dip near Tonga, the fingerprint of the hole. This mattered for practical reasons. Disturbances in the ionosphere can mess with the accuracy of navigation systems and with radio communication. When the charged layer gets scrambled, signals passing through it can wobble and shift. For everyday phone navigation, the effect is usually small, but for jobs that need extreme precision, like certain kinds of surveying, farming, or mining that rely on pinpoint satellite positioning, a scrambled ionosphere can cause real trouble. So understanding these disturbances helps scientists warn people who depend on that precision. The hole was only the opening act, though, because the eruption did more than punch a gap in the electric layer. As the disturbance spread and grew, it seeded something far larger and stranger, a kind of disruption that reached even higher, stretching up toward true outer space and interfering with satellites orbiting the Earth. These strange structures have a name, and they climbed to heights that left scientists reaching for words to describe just how far this one volcano had thrown its influence. Above the hole in the electric layer, the eruption seeded giant structures that climbed toward outer space. Scientists call them equatorial plasma bubbles. The word plasma here just means that electrified air, the charged gas that fills the ionosphere. A plasma bubble is a region up in that layer where the charged particles thin out and behave in a wild, patchy way, full of small-scale swirls and gaps. These bubbles form near the equator, and normally they appear on their own, tied to the daily rhythms of the upper atmosphere. They matter because their patchiness can scramble satellite signals passing through. After the Tonga eruption, an enormous plasma bubble appeared over the Asia-Pacific region. The pressure waves from the blast racing upward and outward disturbed the ionosphere so strongly that they helped trigger one of these bubbles. And this was no ordinary bubble. Using a satellite built to study the space around Earth, along with ground stations tracking the ionosphere, scientists found the disturbance stretch far higher than expected. It reached up to an altitude of at least 1,200 miles above the surface. Let that height sink in for a moment. 1,200 miles up is well beyond where most people picture the atmosphere ending. It is far above where the space station orbits. It reaches into the region where satellites circle the Earth. A volcano at the bottom of the Pacific Ocean had sent its influence more than 1,000 miles into space, disturbing the charged environment where spacecraft fly. That is a reach almost beyond imagining for a single eruption. The size of the bubble surprised the scientists studying it. Earlier research had suggested that plasma bubbles reaching such high altitudes were rare. Standard ideas about how these bubbles form did not predict one climbing this far. The Tonga bubble stretched well past what the old models expected, forcing scientists to admit their understanding had gaps. A volcano had shown them a version of this phenomenon bigger and higher than they thought possible. Why should anyone on the ground care about a bubble in space? Because these bubbles can interfere with the satellites and signals we rely on. When a navigation signal passes through the churning, patchy plasma of a bubble, it can flicker and distort. This can throw off precise positioning and disrupt certain radio communications. As more and more of daily life leans on satellites, understanding and predicting these bubbles becomes more important. The Tonga event gave scientists a dramatic real-world example to learn from. So the eruption had now reached from the deep sea floor all the way up past the edge of space, disturbing the electric skin of the planet and seeding a bubble that climbed toward the satellites. But hidden inside all this data was the strangest twist of all. When scientists looked closely at the timing, they noticed something that did not fit. The disturbances high in the ionosphere seemed to begin before the shockwave from the eruption could have reached them. The effect was arriving ahead of its own cause. That impossible-sounding detail was about to overturn a piece of what scientists thought they knew about how the ground, the air, and space are connected. When scientists lined up the timing, they found something that made no sense at first. The disturbance in the upper atmosphere started before the wave from the eruption arrived. Here is why that seemed impossible. The pressure wave from the blast travelled upward and outward at a certain speed, roughly the speed of sound near the ground. Scientists could calculate when that wave should reach any given spot, including high up in the ionosphere, so they expected the electric layer to react only after the wave got there. 'Cause first, then effect. That is how the world is supposed to work. The data showed the opposite order. High in the ionosphere, the charged air began to stir several minutes to even hours before the pressure wave from the volcano should have reached that altitude. The electric layer twitched early, as if it somehow knew the wave was coming. Sudden changes in the density and height of the charged air appeared ahead of schedule, arriving too soon to be explained by the ordinary wave creeping up from below. So what was carrying the message faster than the wave itself? Scientists worked out an answer that reveals how deeply connected our planet's layers really are. The eruption did not send just one kind of wave. It also launched faster atmospheric waves that raced upward quickly and reached the ionosphere ahead of the slower pressure wave. Once those fast waves disturbed the charged particles high up, the effect could spread even faster still, because charged particles can pass energy along the planet's invisible magnetic field lines at great speed. Energy leapt along those magnetic lines, letting the ionosphere react before the main wave arrived from below. In other words, the volcano had several messengers, and the quickest ones outran the rest. This finding genuinely surprised the researchers. One scientist leading the work explained that the old picture had to be updated. The models used to describe how a disturbance travels from the ground up into the ionosphere did not include these fast early waves. The Tonga eruption showed that they had to be added, because the upper atmosphere clearly reacted sooner than the old thinking allowed. Think about what this means. The solid Earth, the ocean, the air, and the electric layer near space are all tied together far more tightly than we often imagine. A blast at the bottom of the sea can ripple upward and touch the edge of space within minutes, sending signals ahead through the fast lanes of the atmosphere and along magnetic field lines. The layers of our world talk to each other, quickly, in ways scientists are still learning to trace. The Tonga eruption became a rare chance to study those hidden connections in action. It showed how a single event can reach from the seafloor to the satellites, and how the message can travel by more than one path, some faster than others. By now the volcano had broken records in the water, in the air, on the seafloor, and in space. Yet its longest lasting mark would not be a wave or a bubble or a hole. It would be something the plume carried up and left behind high in the sky. a vast, invisible cloud that would linger for years, quietly changing the atmosphere long after the eruption fell silent. And it was made of the most ordinary substance on Earth. The longest-lasting mark the volcano left was made of the most common thing on the planet: water. This surprises many people. When you think of what a volcano spews out, you picture ash, lava, and choking gas. Those are the obvious dangers. But because the Hunger volcano erupted underwater, its blast carried something unusual skyward in enormous amounts: seawater. When the explosion tore through the shallow ocean, it flashed a huge volume of seawater into vapor and hurled it high into the atmosphere along with everything else. And the amount was almost beyond belief. Scientists using a satellite instrument that measures water high in the atmosphere started seeing readings that looked broken. The numbers were so high they seemed impossible, far above anything the instrument had recorded before. The team had to carefully double-check every measurement to make sure the readings could be trusted. They could. The eruption really had blasted that much water into the sky. When they added it all up, the figure was staggering. The volcano injected roughly 146 million tons of water high into the atmosphere, into the calm layer above the weather. 146 million tons of water vapor, lofted miles above the ground in a single eruption. Where did all that water go? It rose with the plume into the stratosphere, that quiet layer above where jets fly, and much of it spread out and stayed there. Unlike water in the low clouds that rains out within days, water this high has no easy way to fall back down quickly. The stratosphere is dry and stable, so once the water arrived, it lingered, drifting and spreading around the planet month after month. This was different from almost every other big eruption in history. Most giant eruptions are famous for pumping out a certain gas, a sulfur gas that forms a haze and cools the planet for a while. Water is usually a minor part of the story. The Hunger eruption flipped that script. It released a fairly modest amount of the usual sulfur gas, and instead flooded the upper atmosphere with water on a scale never seen in the age of satellites. For once, water was the headline, the main character in what the eruption did to the sky. Scientists had watched a couple of other eruptions send a bit of water that high before, small amounts that faded fast. Those were tiny compared to this. The Hunger water injection dwarfed anything on record in a class entirely its own. Why does a bunch of water high in the sky matter? Because the stratosphere is a delicate, finely balanced place, and it helps control the climate and protects life below. Suddenly adding a vast amount of water to it can change its temperature, its chemistry, and the way it behaves, with effects that ripple out for years. Scientists knew right away that this water was going to be important, and that it would take a long time to fully understand. To grasp just how much water we're talking about, though, a number like 146 million tons is hard to feel. Our minds go numb at figures that big. So scientists reached for a comparison anyone could picture. They measured the volcano's water not in tons, but in something you've probably swum in: swimming pools. And the count they came up with was almost cartoonish. To make sense of the water, scientists imagined filling swimming pools with it, the big ones used in the Olympics. An Olympic swimming pool holds a lot of water. It is 50 meters long, wide enough for many lanes, and deep enough to dive into. Picture standing at the edge of one, looking down its length. That is a serious amount of water. Now try to imagine filling one after another after another. The Hunger eruption blasted enough water into the sky to fill about 58,000 of those pools. 58,000 Olympic swimming pools, launched miles above the ground into the calm layer above the weather. If you tried to walk past that many pools lined up in a row, it would take you the better part of a day just to reach the end. All of that water taken from the ocean in an instant and thrown into the upper atmosphere by a single blast. And it did not simply pass through and leave. Once all that water spread out across the stratosphere, it raised the total amount of water in that entire layer, all the way around the planet, by about 10%. Stop and think about that. One eruption, in one spot in the South Pacific, increased the water content of a whole layer of Earth's atmosphere, worldwide, by 1/10. A single volcano nudged the makeup of the sky across the entire globe. This kind of change does not fade in a week or a month. Water that high up leaves only very slowly, drifting and mixing over long stretches of time. Scientists tracked the extra water as it spread from the tropics toward the poles and lingered season after season. Years after the eruption, they could still measure the extra moisture up there, a fading but stubborn reminder of the blast. Reports noted the water was still present well into the following years, refusing to fully clear out. For scientists, this created a rare and valuable situation. They now had a huge, measurable change to the atmosphere, one they could watch evolve over years. By following the water, they could learn how the stratosphere moves and mixes, how moisture travels through it, and how it slowly leaves. The eruption became a natural experiment on a planetary scale, teaching lessons that no laboratory could ever provide. But this experiment came with real stakes for the climate. Water high in the atmosphere is a greenhouse substance. It traps heat. So many scientists expected the flood of stratospheric water to warm the surface of the planet, at least a little, for a few years. Some worried it might even nudge global temperatures upward at a delicate moment, pushing them past an important line that countries had promised to try to stay under. The world's climate scientists watched closely, bracing for extra warming from the volcano's water. Then the measurements came in, and the volcano delivered a genuine shock. Because instead of warming the planet the way so many had predicted, this eruption did something almost no one saw coming. It went the other way entirely. Everyone expected the volcano to warm the planet. It did the opposite. The reasoning behind the warming prediction was sound. All that water blasted into the upper atmosphere traps heat, the way a blanket holds warmth against your body. With the stratosphere suddenly 10% wetter worldwide, many scientists expected a small but real push toward higher temperatures. Some even feared the eruption might help shove global warmth past an important threshold that the world's nations had pledged to avoid crossing. So scientists ran the measurements and the models, expecting to see warming. What they found, after careful study, was that the eruption actually cooled things, at least across the southern hemisphere, the bottom half of the planet closest to the volcano. One research team calculated that the blast lowered temperatures there by a small amount, around 1/10 of a degree. The volcano had leaned on the planet's temperature in the wrong direction from what almost everyone predicted. How could an eruption that added heat-trapping water end up cooling the planet? The answer came down to a battle between two effects. On one side, the water tried to warm things by trapping heat. On the other side, the eruption also released that sulfur gas, which forms tiny droplets high in the sky. Those droplets act like a thin sunshade, reflecting a little sunlight back into space before it can reach the ground and warm it. The eruption set up a tug of war. Water pulling toward warming, the sunshade pulling toward cooling. For the Hunga eruption, the cooling side won. Scientists discovered that the tiny reflective droplets this eruption made were unusually small, and small droplets turn out to be especially good at bouncing sunlight away. That efficient sunshade effect outweighed the warming from the water. On top of that, the water and the sulfur interacted in ways that kept the warming from taking over. Add it all up, and the net result tipped toward cooling, the opposite of the fear. The effect was gentle and did not last forever. The overall change to how much heat the planet kept was small, and by a year or two after the eruption, most of these effects had faded as the sulfur droplets cleared out. But the lesson stuck with scientists. They had been braced for warming and got cooling. The atmosphere had behaved in a more surprising, more tangled way than the simplest prediction suggested. This became a humbling reminder. The climate is a web of interacting effects, and pulling on one thread can tug others in ways that are hard to foresee. A flood of warming water can be overpowered by an efficient cooling haze. Real understanding meant measuring carefully and being willing to be surprised rather than trusting the first easy guess. The temperature story turned out to be only one piece of how the eruption reshaped the sky, though. Because that same flood of water high in the atmosphere was quietly working on something else, something fragile and precious that shields every living thing on the surface from harmful rays. The extra moisture was reaching toward the protective layer that guards life on Earth, and it was about to leave a mark there too. High in the atmosphere sits a fragile shield that protects every living thing below, and the volcano's water reached up to thin it. That shield is the ozone layer. Ozone is a form of oxygen gathered in a band high in the stratosphere, and it does a vital job. It soaks up much of the harmful part of the sunlight, the invisible rays that can burn skin, harm eyes, and damage living things. Without the ozone layer, life on the surface would face a punishing dose of that radiation. It is one of the quiet guardians that make our planet livable. The ozone layer is also delicate, and certain chemicals in the sky can eat away at it. For decades, scientists have watched a thinning of the ozone over the frozen south, near the bottom of the planet. Each year, a gap opens there, often called the ozone hole, then heals again with the seasons. The size of that hole changes from year to year, depending on the chemistry and the winds high above. A bigger hole means more harmful radiation slips through over that region. The Hunger eruption's flood of water reached into this delicate system. Water high in the stratosphere can speed up the chemistry that destroys ozone, and it can also cool and shift the winds up there in ways that make the yearly ozone hole worse. As the volcano's water spread across the planet and drifted toward the poles, scientists watched to see what it would do to the protective layer. It took time for the water to travel that far, but eventually it arrived over the frozen south. Scientists connected the volcano to an unusually large ozone hole. In the couple of years after the eruption, the yearly ozone hole over the south grew notably large, and researchers linked at least part of that to the extra water the volcano had added. Some scientists had even predicted this well in advance. Using their models, they forecast that the volcano would help enlarge the ozone hole in a particular year, once the water had enough time to reach the polar sky. When that larger hole appeared roughly on schedule, it matched their prediction. There is an important balance to strike here. Some careful studies found the volcano's effect on the ozone was real but modest, one influence among several that shape the hole each year. The natural year-to-year swings are large, and untangling exactly how much the volcano added takes painstaking work. Scientists debated the size of the effect, and that debate is part of how science sharpens its understanding. Still, the broad lesson held. A single eruption could reach up and disturb the shield that guards life on Earth, at least for a time, by flooding the high sky with water. This raised a bigger worry among researchers. If the volcano's water could stir the ozone and tip the planet's temperature, what else might it be doing to the sky? Might it be nudging the weather itself, the rain and the winds and the seasons that people live by down here where we actually feel it? Scientists began to suspect that the fingerprints of this one eruption might show up in strange weather far from Tonga, in seasons that arrived wetter, drier, or stranger than they should have, and they set out to hunt for those fingerprints. Scientists began to wonder if the volcano's water was quietly tugging on the weather itself, in places far from Tonga. The idea made sense in theory. That vast blanket of extra water high in the atmosphere changed the temperature and the winds up there, and the high atmosphere is connected to the weather down below. Nudge the upper sky, and the effects can trickle down, shifting where storms form, how much rain falls, and how warm or cold a season turns out. So researchers ran climate simulations to see whether the Hunger water might leave a mark on ordinary weather. Their computer studies suggested it could. In one type of experiment, scientists ran a climate model twice. In the first run, they let the world proceed with no volcano. In the second, they added the volcano's huge load of water to the high atmosphere and nothing else. Then they compared the two. Any difference between them had to come from the water. This clean comparison let them isolate the volcano's fingerprint on the weather. The differences that showed up were intriguing. The simulations pointed to the volcano's water helping stir up unusual weather patterns for years after the eruption. Some studies suggested it could tip certain regions toward warmer winters and others toward cooler or wetter seasons, shifting the odds of how a given year would play out. In particular, researchers linked the water to a wetter than expected stretch of weather in certain places, and to lingering effects that could ripple through the seasons for the rest of the decade. It is important to be careful here. Weather is influenced by countless things at once, from ocean patterns to the natural swings of the seasons. Teasing out how much a single volcano contributed is genuinely hard, and scientists are careful to say so. The volcano was one nudge among many, not the sole cause of any one storm or warm spell. Its overall effect on the global average temperature, for instance, was very small, a tiny fraction of a degree. Still, the broad picture was striking. A single eruption in the South Pacific may have subtly shifted the odds of weather patterns around the world for years, all through the water it lofted into the sky. The rain that fell on distant countries, the warmth or chill of their winters, might have carried a faint echo of a volcano that erupted far away. It is a humbling thought, that one blast could reach into the seasons of your own hometown. This became one more way the Hunger eruption connected everything. The sea, the air, the electric edge of space, the protective ozone shield, and now perhaps the weather in your backyard. A single event had reached into nearly every part of the planet's system and would keep teaching scientists for years to come. Yet for all the records the eruption set, one basic puzzle still nagged at researchers, a piece that did not fit the usual picture of a giant blast. This eruption had been enormous, one of the most powerful in a century. But when scientists looked for a certain gas that such a massive eruption should have released in huge amounts, they found surprisingly little of it. The volcano was hiding something, and the mystery of the missing gas is still not fully solved. For all its size, the eruption held back on something a giant blast is supposed to produce in floods: sulfur. To see why this is strange, you have to know what usually makes a volcano affect the climate. The big, famous eruptions of the past are remembered for pumping out enormous amounts of a sulfur gas. High in the sky, that gas turns into a haze of tiny droplets that reflect sunlight and cool the planet for a year or more. The bigger the eruption, generally, the more sulfur it releases, and the stronger its cooling punch. Sulfur has long been the main character in the story of how volcanoes change the climate. The Hunger eruption broke that pattern. By almost every measure of raw power, this was a monster. The tallest plume ever recorded, the loudest blast in over a century, energy rivaling hundreds of atomic bombs. You would expect such an eruption to belch out a staggering load of sulfur gas. Instead, when scientists measured the sulfur, they found a surprisingly modest amount, far less than a blast this violent seemed to promise. The numbers did not match the fury. This puzzled researchers. A giant eruption with only a middling amount of sulfur is unusual, and scientists have worked to understand why. Part of the answer likely ties back to the volcano being underwater, and to the odd chemistry of how it erupted. Some of the sulfur may have ended up trapped in the sea rather than the sky. The way the water, rock and gas interacted in this strange, wet, explosive setting may have kept the sulfur output lower than the eruption's size would suggest. The details are still being studied. The low sulfur helped explain another surprise from earlier in this story. Remember how scientists first feared the eruption would warm the planet through its water, then discovered it slightly cooled instead. The sulfur played a key role in that twist. Even though the amount was modest, the tiny reflective droplets it formed were unusually small and efficient at bouncing away sunlight, and that cooling edged out the warming from the water. So the sulfur, small in quantity, still swung the outcome. A little of it, in just the right form, tipped the balance. There was another loose end too. The extra water high in the sky lingered longer than some models predicted, spreading and staying up there in ways that did not perfectly match the expectations. This told scientists that their picture of how the high atmosphere moves and mixes still has gaps. The eruption kept handing them puzzles, pieces that did not quite slot into the existing understanding. That is part of why this single event has been studied so intensely. It behaved differently from the giant eruptions scientists thought they understood. Low on sulfur, drowning in water, cooling instead of warming, reaching higher and farther than any before it. Each surprise forced researchers to sharpen their ideas and admit how much they still have to learn about volcanoes and the sky. By now, years have passed since that violent January day. The waves have long since settled. The plume is long gone. The pressure that circled the globe faded away, but the volcano itself is still down there, deep beneath the Pacific, and it is not finished. In the quiet dark of the seafloor, the giant has already begun, slowly and patiently, to do the one thing it has always done best. The volcano did not die when it blew its top off. It is still down there, and it is already rebuilding. After the great eruption, the mountain fell quiet. The island that had stood above the waves was mostly gone, blasted away and collapsed into the sea. From the surface there was little left to see, just open water and a few battered scraps of rock where a green island had once been. It might look like the story ended there, with the giant spent and silent. But volcanoes like this rarely stay finished. Deep below, the mountain still sits over its source of melted rock, in the same violent zone of the planet where slabs of crust grind and dive. The fuel that powered the eruption has not vanished from the Earth. Over time, melted rock can gather again in the chambers below, slowly refilling, the way it did in the years before the last blast. The giant is wounded, hollowed out at its centre, and yet fundamentally still alive. Scientists have kept watching it closely. Research ships have mapped its reshaped seafloor. Instruments have listened for rumbles and tracked its restlessness. And in the time since the Great Eruption, the volcano has shown small signs of ongoing activity, quiet stirrings that remind everyone the giant is merely resting, not gone. It has done this before. It built land in earlier eruptions, then destroyed it, then built again. The cycle is part of its nature. There is a real chance the island itself will one day return. The volcano has proven more than once that it can push new ground up out of the open sea. Given enough time and enough eruptions, a fresh island could rise again where the old one stood, rebuilt from ash and rock, only to face the pounding of the ocean once more. The mountain is a builder and a destroyer in turn, endlessly remaking the little patch of sea it calls home. This ongoing life is exactly why scientists refuse to look away. They want to understand how the giant recovers, how fast the melted rock returns, and whether the next eruption might be gentle or violent. Watching the volcano heal and stir gives them a rare, continuing lesson in how these underwater monsters work. And it keeps them alert, because a volcano that did so much last time deserves close attention as it wakes toward whatever comes next. For the people of Tonga, who live in the shadow of this giant, that vigilance matters deeply. They rebuilt their lives after the eruption, repaired their cables, cleared the ash, and carried on. But they share their corner of the ocean with a mountain that has shown its terrible power. Knowing more about it, watching it, understanding its moods, is part of how they stay safe in the years ahead. The Hunger Volcano, then, is a story that has not ended. It has only paused. The giant sleeps again in the deep, gathering its strength in the dark, patient as ever. And what it did during those hours in January changed far more than one island. It changed what scientists believed a volcano could do at all. When they finally stepped back to take in everything this one eruption had accomplished, they realized it had left them with a warning they could not ignore. When scientists gathered up everything this one volcano had done, they realized it had rewritten the rulebook. Think back over the trail of records. This eruption threw the tallest plume ever measured, punching past the stratosphere and into the edge of space, the first volcanic cloud ever seen to do it. It sparked the most intense lightning storm ever recorded, with bolts firing higher than any caught before. It fired a blast heard nearly 6,000 miles away, one of the loudest sounds in over a century. And that was only the start of the list. It sent a wave of pressure circling the entire planet at least 5 times. It raised a tsunami across the whole Pacific, then reached through the air to raise the sea and oceans it does not even touch. It unleashed the fastest underwater flow ever recorded, powerful enough to run uphill and cut a nation off from the world. It punched a hole in the electric layer near space and seeded a bubble that climbed toward the satellites. It flooded the high sky with water, cooled the southern hemisphere, and left fingerprints on the ozone and perhaps the weather for years. No single eruption in the age of modern science had ever done so much, in so many places at once. That is why researchers keep calling the Hunger eruption a wake-up call. For a long time, most attention went to volcanoes on land, the ones people can see and climb and watch. The great underwater volcanoes scattered across the ocean floor drew far less notice. They were hard to reach, hard to study, and easy to overlook. The Hunger eruption showed, in the most dramatic way possible, how dangerous that blind spot could be. The lesson landed hard. Underwater volcanoes, especially the shallow ones where seawater can meet magma and explode, can produce blasts and tsunamis that rival or exceed the worst eruptions on land. Their reach can span the entire globe, and most of them are barely watched, their moods a mystery, their next moves unknown. The ocean hides an unknown number of these giants, and the world had been paying them too little attention. Scientists took the warning seriously. The eruption pushed researchers to study underwater volcanoes more closely, to map more of the seafloor, to improve the tools that watch for eruptions, and to rethink how tsunami warnings work when a volcano, not an earthquake, is the cause. Every strange record the Hunger blast set became a clue, teaching scientists how these events unfold and how to spot the next one coming. There is something humbling in all of this. A mountain most people had never heard of, hidden almost entirely beneath the waves, reached up in a single afternoon and touched the whole planet from the seafloor to the edge of space. It reminded us how much power lies waiting in the parts of our world we rarely look at, and how much we still have to learn about the ground beneath the sea. The giant sleeps now, healing in the dark, gathering itself for whatever comes next. Somewhere out there, in the vast quiet of the ocean, other giants like it wait too, unmapped and unwatched. And the next time one of them wakes thanks to a January day in Tonga, we will be paying far closer attention.